Okay, let's start today's class. So before starting today's class, I will briefly review what we learned in the previous class. Okay. In the previous class, we learned about the abstractions in computer systems. So I said that the concept of the abstraction is very important in computer engineering and then computer science area. So it is because the computers are complicated system. It's a very complex system. So it's not possible to understand the entire thing inside of the computer system. Also, the computer systems are composed of software and hardware. So if we only focus on the software is composed of application software and system software such as a compiler and operating system. So in order to understand the computer systems, we divide this entire computer system as many layers like this figure, okay? So, and then we just try to focus on a certain layer. So for this course, we will focus on the architecture and microarchitecture layers, okay? And then, so we will focus here. Also, in order to understand some interaction between adjacent layers, we need to also understand the interfaces between neighbor layers. So for example, so in this course, we will focus on the architecture, but we will also study the interfaces between architecture and operating systems, but slightly, not entire thing about the operating system. So it's some kind of concept of abstraction. Also, I explained the examples of abstraction in the computer processors and then computer systems, like this abstraction, so microarchitecture and the systemical view of the computer systems, okay? And then we briefly learned about some semiconductor technology and then chip manufacturing process because the CPU is a chip, it's a digital chip. So and then we already know that the semiconductor industry is very important. And also actually the semiconductor technology leads the technology under our computer systems or processor chips. So, okay. Any questions about the previous class? Okay. Okay. So before starting today's class, where is it? Here. So this is the blackboard. So blackboard of the Korea University. And then as you can see, I added some links for it's a Zoom classroom. And then this is the Piazza. So if you click the Piazza link, then you can enter the Piazza Q&A page. And then so you can post any questions or any issues regarding the homework, exam, and then also regarding what we learned during the classes, okay? So click new post, and then you can post anything. And then you can use English or you can use Korean, okay? And then if you click the resource link here, then you can find the lecture notes here and the lecture videos here. So I will post the link of the YouTube video here. So like day 1, so introduction to the course, day 2, the abstraction we learned in the previous class. So then I try to post the YouTube video before the end of the day, but if I am busy, then I can post the YouTube video in the next day or the next day. So So in the today's class, we learned about the performance of a computer system. So in this time, we will learn about the how to measure the performance of the computer system or computer processors. So in the previous class, we learned that computer runs software. And then computer is composed of actually the software and hardware. So we need to consider the both software and hardware to measure the performance of computer systems. Because we learn software on computer hardware. If the hardware performance is not good, then the performance of the entire computer system will not be good. Okay, that's obvious. And then let's think about the software. Software is very bad, so it's a bad software. Then what is the entire performance? Entire performance will be also bad because it's the bad software. So when we talk about the performance of entire computer systems, we need to focus on the both software and hardware. Okay, and then I will take an analogy about the performance of some systems. So this is the analogy of the airplane, and then each graph shows the performance. Some specific category of or some specific feature of airplane. So this graph represents the passenger capacity of the 4 different airplanes, like Boeing 777, 747, something like that. And then how about this graph? It's the cruising range. So there is some distance which can fly in the one flight. Okay, and then the third graph represents the speed. And then what is this fourth graph? This fourth graph represents the number of passengers multiplied by mph, is a mile per hour. That is the cruising speed. So that is the some multiplied value. So let's assume that you are the CEO of the airplane company. So it's an airplane company. Then you want to buy some airplanes for your company. So what should we consider for the performance of airplane? So I said that in this slide. So this slide represents the 4 different categories of the performance for the airplane. So actually this first performance metric is the multiplication of the number of passengers and speed. So it's some combined performance metrics. But so we can consider the number of passengers and then some distance and then speed, or we can combine 2 different metrics and then generate the one performance metric. So which should be considered if you are a CEO of the airplane company? So if you focus on the capacity, so there's a number of passengers, then we need to consider these metric, like the passenger number of people which can be transferred in one airplane. Also, if you just focus on the distance, then we need to consider this metric. The speed is the kind of performance. But if you just consider some combined performance, such as so we need to consider also the number of passengers which can be transferred by this one airplane. Also, we need to consider the flight time. So that is the speed. So if we consider these two different metrics, then we can combine these two metrics. So we can also calculate the passengers multiplied by speed of the airplane, and then we can also measure these performance metrics for the different airplanes. So this is some example of the performance. So the main topic in this slide is that the main theme of this slide is that the metric. So we can define the different performance metric, but this performance metric is determined by purpose of some systems. So if we consider the number of passengers, then we will consider this metric. But if we consider the time, so cruising speed, then we need to consider this metric. So if we need to consider the combined metrics, like combined performance, then we need to measure this metric. Okay, it depends on the purpose of systems. Okay, actually this is the airplane, and then we are learning about the computer system. So we need to consider the performance metric of the computer system. So if we buy some new computer machines, like or new computer smartphone, which factor will be considered? So for example, so your laptop computer is so old, so you want to buy the new one, and with maybe some cost, but which factor will you consider? So actually, this is the new laptop, so I think everyone will consider performance. And then when you mention the performance of your laptop, then what does that mean? The performance of a laptop, yes, right, it's the speed. So then we frequently mention that, oh, my laptop is faster than your laptop. So my laptop is better than yours. So we frequently mention speed or it's fast. So when we measure the performance of our computer system, we first consider the response time. So response time is that it's the time from start of the application to the end of the application. That is the response time. So simply it's the start to end time. Okay. And then also we can consider some different performance metric called throughput. So actually the throughput is somewhat different from the time. Actually response time, for response time, we focus on the time. That means the speed. And then when we mention throughput of the computer system, then we focus on the amount of workload. That is the amount of work which can be done in the unit time. It's the definition of the throughput. So we can focus on the time, or we can focus on the amount of workload. So there are two different metrics. So okay. So definition. So this is very important. Just you need to differentiate the definition of the response time. It's frequently called the latency. So latency means the time between start and end of the application. So how long it takes to do a task. That is the definition of a response time. And then another performance metric is the throughput. So the definition of the throughput is the total work done per unit time. Okay, so that is the two different performance metrics in computer systems. So for the response time, we just measure the time, like the second, millisecond, microsecond. It's a unit of the time. So for the latency or response time, we use the unit of time. And how about the throughput? The throughput is the amount of work done during the unit time. So throughput is the unit of the throughput is something like megabyte per second, where MIPS, we can frequently use the flops, like a floating. Okay, so that means the floating number of floating operations per second. So we will learn later about these flops. So for the throughput, so we just measure the amount of work per second. So we need to differentiate these two different metrics. So then how can we increase the performance of computer system? Okay, how? So if we focus on the response time, then how can we improve the performance of this computer system or computer processor? It's a faster computer. So if we just mention the faster computer, then we frequently mention the response time. So, and then when we mention the faster computer, then that means the computer which have faster clock, like 2.0 gigahertz clock or 3 gigahertz clock, 2.4 to 3 gigahertz clock. So we already know that if the computer processor runs with the faster clock, then there is a usually faster computers. So then if we just focus on the throughput, so amount of work, then we can focus, how can we improve the performance of a computer system? More processors. So when we purchase a laptop computer, and then we just focus on the performance of the CPU. And then one CPU has the single core, and then another CPU B is CPU A, has the some quad core. So that means the 4 cores. So which one is better? The CPU which have multiple cores, like 4 cores, because with the multiple cores, we expect that this computer will process more work in the same time, because there are more workers. Okay, so if we focus on this response time, we can increase the clock frequency, and then if we focus on the throughput of the computer system, we add more processors or more cores. Okay. This is the very important concept, the response or latency, and then throughput. So please memorize these two different concepts of the performance. Okay. And then let us focus on some latency, that is the response time of computer systems, because I said first I mentioned we frequently use faster, but that means the response time of the computer system. So we frequently mention the execution time or speed of the computer systems for comparing performance of two different computer systems. So we will focus on the response time of the computer system. So first, we need to define what is the performance of a computer system. So I mentioned that if the computer is slow, slow means the execution time is long, right? And then if the computer is fast, then execution time is short. So we can say that this slow computer is the performance is low, and then for this fast computer, performance is high, right? So we can know that it's very easy. Performance is inversely proportional to the execution time, right? So we can say that if the execution time is short, then that means performance is high. And then reversely, if the execution time is long, the performance is low. So performance is inversely proportional to the execution time. So we define the performance of a computer system is 1 over execution time. So the unit of the execution time is can be the second, 1 microsecond, 1 millisecond. Okay. And then if we compare the performance of the two computer systems, then we can measure the execution time. And then if we just compare the two different performance of two different computer systems, we just compare the ratio of performance of two systems. Okay, so we frequently say that computer X is n times faster than computer Y. So it's the same. So if the system is not a computer, then we can frequently say that system A is n times faster than system B. So in that case, we just compare the performance with the ratio of two performance metrics. So if we just say like this, then N means like this, performance of X over performance of Y, right? And then we learned that the performance is inverse of execution time. Then this means execution time of Y over execution time of computer X. Why do I explain like this? So actually, we can easily measure the execution time of the computer system. It's just a measure. It's just a measurement. So we can just measure the time gap between start to the end. And then performance is defined as the 1 over execution time, the inverse of the execution time. So first, we need to measure the execution time of a computer system X and then computer system Y. And then we just compare the performance like this, like this, okay? That's why I explain like this, okay? Understand? Okay, so this is the example. And then let us assume that with the computer A, the execution time of the same application, so it's the same program. So with the computer A, it takes 10 seconds. So 10 seconds. So 10 seconds means the execution time of A. And then the execution time on computer B is 15 seconds. And then the problem is a real problem in the exam. So just compare the performance of these two computer systems. So it's the same. So very easy actually. So if we just measure this performance, compare the performance, then we can use this equation. So 15 seconds, that is the execution time by computer B over execution time of computer A is the 1.5. So we can say that like this sentence. Computer A is 1.5 times faster than computer B. It's easy, right? It's easy. So but I actually performance is the very important part of the computer system. Actually, in the chapter 1, performance is the most important topic of the chapter 1. So I frequently make some exam problems to compare the performance of two different systems. And then actually the definition is easy, but many students fail to write the right answer, fail to write the correct answer, even though the definition is easy. So I explained very easily about the performance of a computer system like this. So just to remember that performance is inverse of the execution time. That is the start point. Okay. Then how can you measure the execution time? So I said that not to compare the performance of two different computer systems, we need to measure the execution time. And then I said that, oh, it's easy. It's a time gap between start and end of the application. So we can just measure the entire elapsed time. It's the total execution time when we push the enter key for some application, and then can just measure the execution time until the end of this application. So that is the elapsed time. But in the previous class, I explained that the computer is the very complex system. So actually the computer system, the entire computer system is composed of many different components like processor, memory, input and output devices. Also, our application, like this user application, runs on the operating system. So this system is very complex, and then it's composed of many layers. So if we just measure some elapsed time of our application, then many different factors are included in this elapsed time. So for example, we can just push the enter key, then the computer system need to process this event of pushing enter key. That is the kind of interrupt. So it will take time. Also, operating system need to manage the different processes or different applications. So operating system overhead will be included in the entire execution time. Also, the idle time or some other different factors will be included in this entire elapsed time. So with this elapsed time, it's not easy to compare the two different performance of two different processors or CPUs fairly, because many factors will be included in this entire elapsed time. So if we focus on some performance of a processor or performance of a CPU, then we just measure the CPU time. So CPU time means that we just exclude these overheads. So some different factors are excluded in the this entire elapsed time. So CPU time means that this software, actually the software is compiled and then the instructions are generated from the software. And then these instructions are stored in the main memory of the computer system. And then these instructions are transferred to the CPU. So just ignore these different factors like these overhead, and then we can just measure the execution time by CPU. And then this is called the CPU time. And then in this course, we will focus on the some process architecture. So we will focus on the architecture of the processor such as CPU. So when we compare the performance of the CPU with some processors, we focus on the CPU time. Okay, we focus on the CPU time only because we cannot. It's not easy actually. These are some random factors. It's not just determined factors. So we just focus on the CPU time for this course. Okay. It will make our problem simpler. Okay. Before explain about the CPU time of our software or applications, let's talk about the clock signals. So if you take the digital logic design course, I believe you learned about the clock signal. So actually, every digital system or every chip or every digital circuits works with clock signal. Okay, that means, so this is the what we learned in the digital logic design course. Okay, let's start from here. So this is the D flip-flop, and this is the D flip-flop, and then combinational logic is here, and then clock is connected to the clock port of the D flip-flop. That is the basic implementation of the digital systems. And then it's the combination logic has some delays, execution delays. So this, and then the first D flip-flop gives some input signals to this combinational logic, and then this combinational logic is just like a black box. So it receives the input signal and then generate the output signal after some delay, delta t, right? And then, so at the rising edge of the clock, this clock signal, the input signal is given to this combinational logic. And then after some delay is a delta t, this combinational logic generates the output signal based on these input signals, right? And then these output signals are sampled by clock signal by this flip-flop, this flip-flop. So that means the delay of this combinational logic, the delta t, should be shorter than the period of the clock signal, right? The input signals for this combinational logic should be is prepared at the rising edge of this clock signal. So the clock signal starts from here, and then the output is sampled by the next rising edge of the clock signal by this flip-flop. So that means if the output is generated here, then this D flip-flop will sample the incorrect output signals, because correct output signals will be created here. So in this case, we need to slow down the clock signals. That means the clock periods to be longer. So after delta t, the output signals will be generated here. Then these output signals will be sampled by the next rising edge of the clock signal. That's how the digital systems work with the clock signals. Okay, so that is the very basic of the digital system design. And I believe if you took the digital logic design, then you already learned about this clock signal. Then why clock signal is important for the performance of a computer system? So actually the computer system is CPU, that means the CPU, the computer processor is also kind of digital systems, okay? So computer processor also works with clock signal. And then we assume that in the computer process, so computer processor is also composed of many combinational logics and then many D flip-flops. That means the pipeline registers. So we will learn about these pipelines later. So the CPU, we expect, it's just expectation that always true. We expect that with the one clock, one instructions will be processed by computer processor. So I will repeat. We expect that computer processor execute one instruction per clock. So instruction per clock. And I said it's not always true, but that is our expectation. Because in every clock, this processor reads the instructions from the memory, and then the clock processor generate the output from this instruction. And then at the next clock, processor reads another instruction from the memory, and then generate the output signals or some outputs based on this instruction. That is our expectation. So that means if the clock signal is fast, so that means the clock period is short. If the clock signal is fast, then we expect that this computer processor will execute one instruction faster, right? Understand? Okay. So we assume that the speed of the processor is proportional to the frequency of the clock signal. Okay. And then I believe everyone knows how to measure the clock period and then clock frequency. So clock period is the time between one clock rising edge to the next rising edge of the clock signal. That is the clock period. And then frequency is the inverse of the clock period. So the unit of the clock period is it's the same to the unit of the time, like second. And then the unit of the clock frequency is the hertz. We frequently say it's hertz, but the correct pronunciation is hertz. Okay, so we frequently say the clock frequency is 4 gigahertz and then 3 gigahertz, like this. Okay, so we learned about the clock signal here. Okay, and then let's see how to measure CPU time. Okay, CPU time. So this is the CPU, and then CPU received some instructions, but these instructions are generated from the software, like application. And so we assume that so the CPU just receive the software and then start execution and then end the execution of this software. So CPU time is actually the elapsed time. It's the elapsed time from start of execution to end of execution. So CPU time is the elapsed time from start of execution to end of execution of software. Okay. And how can you measure the CPU time? So we learned that the CPU works with the clock signal. It's a clock signal. So when you measure the CPU time, we can just count the number of clocks to execute a certain software. Okay? I will repeat. We can measure, we can count the number of clocks during execution of software. Okay. So CPU time is simply number of CPU clocks multiplied by clock cycle time, and means the clock period. Obvious, right? And then we can simply express this equation like this: number of clock cycles divided by clock rate. It's a frequency. Okay. So let us assume that if the software for executing this certain software, the number of clock cycles like let us assume that we consume the 4 multiplied by 10 to 9 clock cycles for executing this software. And then the clock cycle time is a period where the frequency of this CPU is the 4 gigahertz, like 4 hertz. I don't know. Hertz. Then the CPU time is just 1 second, right? It's the 1 second. Okay. So it's easy actually. It's obvious. So when we measure the CPU time, we can just count the number of CPU cycles multiplied by clock period of the CPU signal, or we can divide the number of CPU counts with the clock frequency. Why is it important? We can use this equation for improving the performance of CPUs. How can we improve the performance of a CPU? If we see this equation, how can we improve? So how can we increase this number? And obviously, we can increase this part. No. In order to improve the performance of a CPU, then we need to reduce the CPU time. Oh, sorry about that. So in order to increase the performance of this CPU, we need to reduce the CPU time, right? Then how can we reduce this number? So easy, it's obvious. So we can reduce this number, so CPU clock cycles, or we can increase the clock rate. Right. Then how can we reduce the number of clock cycles, or how can we increase the clock rate? Actually, there are many ways to improve the performance of CPUs. But if we see that this equation, we can reduce the number of clock cycles. And then normally this part is done by software or some other part like algorithm, compiler, and then or some instruction set architecture. And then clock rate. So clock signal is determined by this data system implementation, usually delay of the combinational logic. Right. So we learned about the basics of data system design here. So in order to increase the clock rate, that is the part of hardware, because it is related to the implementation of digital systems. So increasing the clock rate. It's the hardware part. Okay, so actually the equation is easy, but we need to explain from this equation. Okay, the equation tells that we need to reduce the clock cycles, number of clock cycles, and then also this equation tells us that we need to increase the clock rate. That is the effort of the hardware, and then this is the effort of the software. So we need to focus on the software and hardware. Okay. Okay. So this is the example of comparing performance of the two systems. It's a little bit different, but let us assume that the computer A has the 2 gigahertz of the clock signal, and then CPU time is the 10 seconds. And then let us assume that you are requested to design new computer, is a computer B, and then the goal of this computer B design is to reduce the CPU time to the 6 seconds. It's less than this CPU time. And then for this design, we need to use the faster clock, right? The CPU time is reduced the 10 seconds to the 6 seconds. And then we learned that the CPU time is the number of clocks divided by clock frequency. So in order to reduce this CPU time, then we need to increase the clock frequency. So we need to use the fast clock, but it will cause 1.2 times more clock cycles. And it is frequently observed. If we use the faster clock, then number of clock cycles can increase. Okay. Then how can we set the clock frequency? So we can just use this equation. The clock rate of the computer B is the clock cycle B divided by clock time of B, CPU time of B, and then this is the goal of the CPU time of the computer B, and then what is the clock cycle of the B? Is the 1.2 times of the clock cycles A, and then we can easily also calculate the clock cycles of A. So clock cycles of A is the CPU time of A multiplied by clock rate of A. It's obvious from this equation. So that is the number of clock cycles in the processor A. And then we can easily calculate this number. 1.2 multiplied by clock cycles of A divided by 6 seconds. Then clock rate of this new computer B should be 4 gigahertz. So compared to the 2 gigahertz, the clock signal is 2 times faster than the computer A. Okay, that is some example problem of the CPU time. And then we will extend this equation. It's a CPU time. And then we can calculate the clock cycles like instruction count multiplied by cycles per instruction. So why we use this notation? Because in the previous slide, I mentioned that, oh, this is the software, and the software is given to the CPU, and then CPU execute this software, and then we measure the time for this execution. But in the computer system, actually, this software is compiled, and then instructions are generated. So this is the instruction. Sorry for bad writing. I frequently write like a inst, and then this is instructions is an instance. Okay, so this is the software, and then software is compiled, and then the instructions are generated from the software. So actually, in the computer hardware, these instructions are executed. So instructions are given to the CPU, and then CPU generate the output. Okay. So actually, instruction count is important. So actually, these instructions are counted, instructions are executed. So we can rewrite the clock cycles like, so this is the instruction count of the software, so number of instructions, and then cycles per instruction. That means the required clock cycle to execute one instruction. It's the cycles per instruction. So that means the required clock cycle to execute one instruction. Okay, then we can easily calculate the clock cycle. So this is we can rewrite the clock cycles like instruction count multiplied by clocks per instruction. And then this is called the CPI. So clock cycles per instruction. Okay. So we can rewrite the CPU time like a instruction count multiplied by CPI multiplied by clock cycle time. So we can rewrite this equation like instruction count multiplied by CPI divided by clock rate. Right. It's obvious. And then we need to also explain from this equation. And then actually, this is the basic equation to measure the performance of a processor. It's a very important equation actually. So we can frequently write like instruction count multiply CPI multiplied by TC. It's a clock period. That is the execution time of a certain processor, Okay. And then why is this equation is important? Because we explain from the equation. Okay, we explain from the equation. It's the same. It's the same to other research field. So if the equation is defined, then we can explain from the equation. So is execution time, oh, I've erased. Execution time is the instruction count multiplied by CPI multiplied by clock period. So there are three factors here. So in order to increase the performance, then we need to reduce the execution time. Then how can we design our computer system? We can reduce the instruction count, or we can reduce the CPI, so cycles per instruction, or we can reduce the clock period. So there are three different factors. Okay. Then how can we reduce the instruction count? Instruction count. So actually, the software is compiled, and then instructions are generated from the software. Then how can we reduce this instruction count? It is determined by software and compiler, because it's compiled. Okay. So in order to reduce the instruction count, we need to design good software. Also, we need to design good compiler. Also, the compiler is designed based on the instruction set architecture. So for example, compiler is designed for x86 architecture with the Intel or AMD CPUs. Also, the compiler can be designed for smartphone processors, and that is the ARM processor. So instruction set architecture also determines the instruction count. So this instruction count is determined by software, instruction set architecture, and compiler. So in order to reduce the instruction count, then first we need to design a good software, or we need to design a good instruction set architecture, or we need to design a good compiler. Okay. And then let's focus on the CPI. So CPI means that it's the cycles per instruction. So that means the number of required clock cycles to execute the instruction. So instruction like add, A, B, C, that means the A equal B plus C. So that is the example of an instruction. And then how did the cycles are determined to execute this instruction? It is determined by hardware. So for example, it's a CPU A, and then this is a CPU B. And then CPU A requires 1 cycle to execute this add instruction. And then also the CPU B requires 2 cycles to execute this add instruction. Then this is bad CPU. So worse CPU. So it is determined by hardware. Also, it is determined by architecture of CPU. Okay. So if we design a better architecture for computer processor, then we can increase the performance, okay, by reducing the CPI number. Okay, and then clock period is obviously it's the clock frequency, and then clock frequency is determined by digital design or some implementation. Okay. So usually this instruction count is the software part, CPI is the hardware part, especially architecture, and then clock period is the hardware part or implementation. So this is some example. This example shows that the computer A, the cycle time is the clock period is a 250 picosecond, 250 picosecond, and CPI is 2.0. B 500 picosecond, CPI is 1.2. The same ISA. And then which is faster? It's just easy actually. So we can use the equation we learned in the previous slide, right? The execution time is the IC multiplied by CPI multiplied by TC. So cycle time is the TC, and then CPI is here, and then same ISA. With the same ISA, if the program is the same, then if the compiler is the same, then same number of instructions will be generated from this same software, right? So I said that software is the same, instruction set architecture is the same, and then compiler is the same. Three factors are the same. Then I see the instruction count will be same. So you need to focus these factors. So I said it's very important actually. Instruction count is determined by software, compiler, and ISA. So these factors are the same, then instruction count will be the same. And then one of the factor is different, then instruction count can be different. So you need to know. So you need to remember this, but it's the same ISA, and then we assume that the compiler is the same. So IC is the same. So we can just compare the CPI and then TC. So CPU time of the A by the equation is like this, and then CPU time B by the equation like this, and then you are requested to compare the performance. So performance A over performance B equal CPU time B divided by CPU time A. So I multiply by 600 picosecond, and then I multiply by 500 picosecond is the 1.2. So that means we learned in this slide, okay? So A is 1.2 times faster than B, okay? You need to say like this. So is it difficult? I think it's not difficult. So if you remember the equation, and then also if you remember the definition of the performance and then some equation and the vectors, then I believe you can easily solve some performance problems. Okay, I believe you can easily compare the performance of two different systems. Okay. Then let's focus on the CPI in more detail. CPI. So actually there are various types of instructions in the computer processor. I said various types of instructions. So in the previous slide, I took an example of add instruction, like add. So we can use the sub instructions, so subtract. And then you can use the multiply, but we can also, the computer system, the computer processor is the different type of instructions, such as the load instruction and then store instruction. So some other kinds of instruction like a branch instruction. So we will learn about these different types of instruction in the next chapter, the instruction set architecture. So, but just to remember that there are different kinds of instructions. Okay, like add submar, load, store, and branch. And then for the different instructions, computer processor may take different number of cycles. So for example, if we just compare the add instruction and the multiply instruction, in the real world, multiplication is more complex than the addition, right? And it's the same to the computer hardware. Implementing multiplication is more complex than implementing addition. Okay. So that means the multiply will take more cycles than add instruction. And then it's the same to the load and store instruction and branch instruction. So the load instruction or store instructions may consume more cycles than this add and sub instruction. The branch is the same. So there are different kinds of instructions executed by processor. And then that means the required clocks for these different type of instructions can be different, maybe usually different. So how can you measure the CPI for this case? So when you consider the different type of instructions, then we can just calculate the clock cycles of the instruction like this. The CPI I is the CPI of instruction I, and then instruction count I is the instruction count of instruction I. And then we just sum for different instructions. That is the clock cycles. Okay? It's obvious. And then sometimes you may be requested to calculate the average CPI. So average CPI is from the definition of the CPI, we can easily calculate the CPI, like average the CPI, like clock cycles divided by instruction count, the overall instruction count. And then that is the CPI over a certain instruction, and then is the rate of this instruction count among total instruction count. Okay, so for example, a certain software is compiled, and then the software has only two instructions, like add instruction and multiply instruction. And then this software has the 40% of the add instruction and then 60% of the multiplication instruction. And then CPI for add instruction is 2, and the CPI for multiplication is for example, 8. So how can we calculate the CPI for this software? It's easy. CPI for add is 2 multiplied by the ratio of this instruction is 0.4, it's a fraction of this instruction count, plus, so CPI of the multiplication is 8 multiplied by the fractions of this multiplication is 0.6. This is the CPI of this software. And you can calculate. Got it? So it is because the different software may have different instruction ratios. Okay. So I said that different software may have different fractions of instructions. And that's obvious actually. For some so for some of software, add is the 40%, but different software may have 60% of the add instruction. It depends on software, okay? So for the different software, then we can calculate the CPI for different software like this. Okay. So this is the example. This is some instruction type. It's an instruction class. So this is instruction A, instruction B, and then instruction C. And then this is the CPI. CPI of the instruction A is the 1, B, 2, C, 3. And then this is instruction count in sequence 1. It's the software 1. So for this software 1, instruction count of the class A is the 2, B1, C2. Instruction count is the software 2. The instruction count for this software 2 is the 4, 1, 1. So for this sequence 1, this is the software 1. The total instruction count is 5, right? 2 plus 1 plus 2. And sequence 2, instruction count is 6. Got it? Then how can we calculate the CPI for the different software? We can easily measure the clock cycles like this. So just one, there are 2 instructions. This instruction will take 1 cycles per instruction. So 2 multiplied by 1. Blah, 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 is 10. The total clock cycles. And then for the software B, it's a sequence 2. The total clock cycles are calculated like blah, 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 9, right? Because and then what is the average CPI? Average CPI is that by definition of the CPI is the total clock cycle divided by number of instructions. Is an instruction count. So total cycles are 10, and then instruction count is 5. So for this software, the instruction count in sequence, For this software, the sequence 1 is the CPI is 2.0, right? And then for this sequence 2, CPI is 1.5. So CPI can be different by different software. It is because different instructions have different CPIs, and then different software has different fractions of these instructions. That's why different software has different CPI value. Okay, so so try to understand this. So there are different kinds of instructions, and then different software has different mixes of instructions. Okay. So we learned how to calculate CPI. Okay. So I will stop here. Any questions? So if you have any questions, then you can turn on your microphone, and then you can ask a question anytime. Okay. Okay. Thank you for listening, and then see you in the next week. Next week. Okay. See you in the next week. Thank you.